Welcome to Digital Futures Young Series live session. I'm Sina Mostafavi, moderating this session on behalf of Digital Future. This session is joined by Digital Futures Young Committee and organizers and Neil Leach. Today's Digital Futures Young session is the third session on computational design, joined by a very interesting lineup of presenters joining us from all over the world. Like all previous sessions, we have live streaming on YouTube and Bilibili, where you can leave your comments and questions. We try to collect them and address them during the discussion after we see all these 6 projects. For updates, you can also visit our websites, digitalfutures.world, where you can find also links to our social media, such as Instagram, Facebook, LinkedIn, Twitter, and YouTube. We also have a live Discord channel. We're going to share the link through the chat box of YouTube and Bilibili. And we would be more than happy if you join our growing community on Discord. Before we start with this session, we would also like to have 2 more announcements. For the next 2 weeks, while we are collecting the entries for the young sessions, we hope to have 2 special events, again on Saturdays, one on the future of education and one on computational design, where we're inviting known scholars and experts. And we would be, again, happy if you follow us for further details about these 2 exciting events. The next announcement is about our next call for Digital Futures Young Series, which will be on robotic fabrication. We hope to share the details of this call right after this session. And we invite you and our community to share the call. And we are already very much looking forward to receiving yours or your colleagues' presentation proposals, which are related to robotic production and fabrication. Okay, to start with the presentation, we invite the first speaker, Jan Kováříček, to share his screen. Jan has graduated from Studio Hani Rashid at the Angewandte in Vienna, University of Applied Arts, and he is currently teaching assistant at Technical University of Liberec in Czech Republic. Jan, you may start. We don't have your voice, I guess.
Yeah, he's on mute.
Yeah, Jan, can you start over again because you're mute?
Now it should work. Can you hear me well?
Yeah, we can hear you.
Sorry. So as I was saying, hello everyone. Thank you for inviting me to present my project Utopian Factory at the Digital Futures Young platform. So the Utopian Factory outlines an alternative to the current model of industrial manufacturing. Leaving behind an excessive production and environmental exploitation of the last 150 years, it embraces key concepts of pre-industrial labor. These concepts are concepts such as highly skilled workforce, sustainable scale of resource harvesting based on local availability, clustering into self-sufficient production hamlets, and avoiding overscaling of the production rate, while being updated with the current possibilities of Industry 4.0, such as automation, which enables mass customization, and the phenomena of digital craftsmanship. So currently, there is hardly more problematic industry in regards of resource exploitation and environmental devastation and a job loss caused by automation than industrial mining. Well, the Utopian Factory investigates a scenario where sustainable timber production offsets the devastation caused by nickel mining. One of the largest nickel mines in continental Europe is located in Finland, and it's called Talvivaara. So within the framework of this project, the Talvivaara mine is considered as a case study of the negative impact of the current industrial tendencies. As you can see on the site, The site is approximately 600 hectares of mining areas, with 240 hectares of primary heap area and 120 hectares of secondary heap area, and the mine refinery. The whole company, the company Terrafame that owns the site and the refinery, is partially owned by the country, by Finland. Nevertheless, there's a huge issues with pollution of the site. Therefore, I'm looking into a sustainable forestry to reintroduce renewable production of timber while reversing the industrial footprint in the area of one of the biggest nickel mines in Europe. I'm devising a remediation strategy which consists of the co-shared forestry model and usage of hyper-accumulating plants for clean nickel extraction and remediation of the devastated land. Therefore, I propose a kind of long-term scenario in which the original heaps that are used to refine to clean the ore that's mined from the open pit mine, I use that to create a new areas for the forestry, for timber for introduction of a forestry. And instead of the original refinery, I'm proposing a combined heat and energy power plant that uses the biomass extracted from the site to produce district energy. The project framework is as following. It's based on 5 steps: remediation, production, process, fabrication, research and development. The remediation is basically using hyper-accumulating vegetation to extract nickel from soil. By this, we introduce slower but non-devastative method of metal mining. The second step is production. Production in the sense of timber farming, which is established in place of original mine extraction areas. The fast-growing biomass is incinerated at district combined heat and energy power plant that's proposed on site, and that produces the renewable heat and energy for the region. The burnt residue is rich in nickel and therefore could be exported as a viable resource of the strategic metal. The processing of resources. So the current digitization of lumber sourcing and forestry allows for effective and holistic resource management and timber production. There are technologies such as satellite IR mapping, automated material inspection for imperfections by lasers that allow for highly effective work with timber. Fabrication. Alongside of the long-term remediation goal of the factory, another of the goals for the factory is to test and develop architectural applications of engineered timber in form of CLT. CLT stands for cross-laminated timber, mass timber constructions. And lastly, research and development, which is basically, we can use these proposed automated production lines to provide an educational ground for retraining blue-collar workers, the original miners of the Terrafame company, in the art of digital craftsmanship, man and robot collaboration, and the research into the phytomining. Phytomining is the procedure of using the plants to extract nickel. So the project facility is located on the north edge of the now disused mine. The goal of the master plan is to embed the fragmented facilities with distinct programs into the slope of the mine to blend with the environment and to eventually stabilize the slope wall of the open pit mine. So to the northeast, we have the wood intake area. Central part consists of bigger production areas, which I'll explain a bit later in the presentation. And southwest part is the smaller training workshops with housing units connected via a system of bridges. As a part of the long-term strategy that I was mentioning, we cover phases for the development of the project in the scope of 7 to 10 years to long-term goals projected for 20+ years. And the factory phases are remediation, that basically establishes new citizen-owned land strategy and terraforming efforts. The research and development, which is focused on retraining the original blue-collar jobs, meaning the miners on site, into a digital craftsman and in the art of using digital tools in the fabrication. And lastly, the production phase, which basically aims to set a trend for slow local production and sustainable production and self-sufficiency. The course of geometry is investigation of the logic of interlocking. It draws inspiration from classical carpentry joining systems and Japanese joinery, but supersizes it into architectural scale of building elements. By following the same rule set of interlocking, we can produce non-standardized construction elements crafted hand in hand by robotic manipulators under the human supervision. These modules are part of larger family of pieces and are compatible across the system. This is done by critically assessing current production process of cross-laminated timber. As much as the production is automated using various CNC machines, it still relies on some sort of a hybrid 2.5D processing space. The counter proposal to it is the full integration of robotic assembly line, not unlike what we see in the automotive industry these days. By using high precision robotic manipulators operating in 3D space, we can achieve more complex prefabricated constructions, compositing interlocking load-bearing mass timber elements with hollow elements that can embed MEP on the needs based on the desired function. The tectonic system that we get by using the interlocking logic is architectonized through introduction of circulation, interior and exterior niches, openings and entrances, and by embedding robotic systems throughout different scales of pieces, effectively blurring the traditional understanding of construction archetypes. By archetypes, I mean things such as post and lintel, construction, column, traditional staircases. The interlocking tectonic language allows for a degree of customization, interiority, size, inline photovoltaic panels into exterior shell by following the logic of cuts. The assembly procedure and the potential is constricted by the structural needs of the system. So there is always a centerpiece, a central element that once inserted braces the complete assembly and braces all the discrete parts in shape. This assembly hierarchy is used for systematic expansion of the programmatic and tectonic functions of the system. What starts as a bracing system of the mine walls becomes an automated factory, which becomes eventually a short-term housing cluster. In here we can see a short-term living and requalification workshop in which the top part is basically the short-term living for the visitors or for the trainees, and underneath as a foundation of the cluster is the collaboration workshop. Over the course of time, based on the effects of reclaiming of the mine and cleaning it up from the nickel within the soil, the phytomining remediation takes course. Eventually, what starts as a fully automated landscape ends up in area cleaned for occupancy of the workers. The short-term housing and workshop district was evaluated for structural feasibility. The CLT has high structural capacity, and therefore, because it's also an orthotropic material, it was proved to be an efficient material of choice, complementing the structural viable tectonics based on polyhedral geometry. With simulated total load of 5 kilonewtons per square meter, the structure achieved displacements around 2.2 centimeters with utilization of around 50% in compression and 35% in tension. The transportation of felled trees utilizes an artificial water channel, which you can see up here in the north in the site in the master plan. The water channel system is used to deliver wood to the processing zone located in northeast of the project site. After quality inspection, cutting and drying the wood is delivered by autonomous cargo fleet to either Eastern automated facility for CLT production, or as formatted wood planks to retraining workshops based on the needs and demands. Those are located in central and western part of the site. So as an energy strategy, I use a combination of the combined heat and energy power plant and kind of a embedded faceted geometry of the project to place photovoltaic panels. So in total, we gather around 1 megawatt-hour of solar energy on roughly 6,000 square meters of surface area. And out of that 1 megawatt-hour is 4/5 of it is provided between March and September, which is based on geographical location of the Finland of the site. The energy compensation strategy consists of alternating between using heat and energy at peak times during the winter from the CHP, the combined heat and energy power plant, and the energy from photovoltaic panels generated during the summer season. This energy chain allows for alternating modes of energy production based on the district needs. So it can, in theory, provide for around 20 kilometers radius worth of villages and small towns, while producing bio-ore rich in nickel during winter. And during summer, producing a CLT. This is a section through a central part of the project in which the research offices, auditoriums, and the automated formatting lines are located. The circulation is differentiated into 3 major streams. The main circulation axis is penetrating the project, connecting east and west exit road out of the mine. The pedestrian circulation, which is both interiorized and exteriorized, and the material circulation, which follows the sequence of the formatting of the wood. Once raw wood is formatted, it is delivered to the large workshop area where a collection of robotic manipulators assemble the engineered timber into a new discrete element. This is done in collaboration of the human operator / trainee. The interior is made from the same mass timber construction system, and it accommodates, as I was showing previously, for this kind of omnipresent robotic manipulators, while also aspiring to be a certain didactic tool reflecting the construction techniques and possibilities of this mass timber construction system. And with that, I would conclude my presentation. Thank you very much.
Thank you very much, Jan. Brilliant work. It's really interesting to see how interesting results are coming from progressive studios at the Angewandte. Brilliant work, congratulations. So I'm sure that there are some questions, but we move to the next presenters. Amin Adelzadeh, who is joining us from Digital Timber Construction Group, DTC at TU Kaiserslautern. Amin has been a lecturer previously in the University of Mazandaran, and he holds a master's degree in architecture, Master of Science degree in architecture from Polytechnic of Milan. So we directly continue with Amin. Can you please share your screen? We don't have your voice yet. Maybe you need to unmute.
What about now?
We have a reflection, so I think you need to
just a second. Yeah.
Unmute the other.
Yeah. What about now?
I think it's good, so you can start sharing probably.
Okay, perfect. So, first of all, thank you so much. It's a great pleasure for me to be here. I am Amin Adelzadeh. As you mentioned, I am a researcher at Digital Timber Construction Group at TU Kaiserslautern. And before starting the presentation, I would like to give you a very brief introduction about DTC, about what we are doing at TU Kaiserslautern. To start with, I have to say that digital DTC, or Digital Timber Construction Lab Group, is an interdisciplinary team of architects, structural engineers, and computer scientists. We are actually exploring, researching, and teaching, innovative architecture and structural system with a good and engineered wood products enabled by digital technology and computational methods. Our major research aim, as you can see, is to use digital design and production methods for more efficient structure using less material, thanks to the smart geometry as well as innovative repeat assembly for simple, fast, and precise construction processes. To be precise, actually, our DTC projects are inspired by the way nature designs structures. Material, our strategy based on this nice sentence. Material is expensive and geometry is cheap. Okay, and according to this, based on this, we have published many researches, and you can find all this information on the DTC website. Okay, and we have a strong contribution to in teaching. We have many workshops, several workshops in different schools, and also we have many academic activities. You can, as you can see here, different interviews, different conferences, and lectures, and so on. You can find this information very easily on the website. And the interesting point is that we also teach, our students at TU Kaiserslautern. As you can see, the interesting point is that what we practice, what we research at DTC are directly used by and exercised by our students at TU Kaiserslautern. To start with, I would like to talk about TSI research, which is it's a kind of ongoing research, which is a key topic for this presentation. Actually, it's focusing on development of a data interface for the automated structural analysis of novel and digitally prefabricated timber structure with a wood connection. Okay, and it's a kind of integration of computational design, structural analysis, and digital fabrication to create a sort of automation in this process. But before instead of talking about this ongoing research, I would like to talk about previous and researches that lay the foundation of what we are practicing now at DTC. And here, as I mentioned, the missing link in digital timber construction chain, which is really important to us. But I will mention in the future in the following pages. So, talking about timber structure, we have to say why wood. Building, as we all know, wood as a building material has experienced a renaissance with city growth in the recent years. Reason for this, or I don't know, many reasons. There would be many reasons, like storage of carbon dioxide, sustainability, economic, and increasing degree of automation, prefabrication in timber construction, efficient transport of light elements. For example, we all know that it has a better strength to the weight ratio and other than materials, and quickly, precise, assembly, so on. There are many reasons, but no one can deny the fact that recent advances in tools and technologies have provided promising opportunity for the realization of this spherical design. You know, for example, this CNC enable architect to reach unprecedented level of accuracy and optimization in and efficiency. And but we have to talk about also the wood products. It's very important because, as you can see, there are many different types of wood products which we use in our construction. We consider it, so it's very important to consider the wood in a wood system, in wood structure, considering the properties, mechanical properties of each product. And talking about just to say about talk about the background, you know, we have to talk about the forbidding wood connections. This is really interesting researches, you know, by the Professor Christopher Robler and also his colleagues at the PFL and ETH. You can find all this information very easily. So, you know, so-called these fitting with connectors in which forces between the components are transmitted through their shapes. Traditional timber construction is widespread, you know, was largely replaced by the mass production metal connectors during the industrialization and so on. But the way they are practicing, the way they had practice actually continued by the DTC, so it's very interesting you know, area. And you may all know that since the 80s, you know, automatic, you know, CNC controls, rendering system have spread increasingly, as I mentioned before, and to realize all these ideas, as I mentioned, it's really important to understand the technology. So we all know that we have to use a language for the numerical control of machine, which is very important. And for this, I would like to mention this interesting plugin by TPS plugin that by Professor Christopher Robler, which is exactly similar to what we are practicing now, because the components that our research or the components we are designing is not published yet, okay, but it is published, and you can find all this interesting information about this TPS plugin. It's free also, and the interesting point is that you know, as you know, that the code used for the machine control programs often referred to geometry code. You know, commonly we call it G code, as we all know that. This plugin can, you know, development of it could create a direct way to produce G code. It's very useful for the complex structure, you know, structures, timber structures, and so on. As you can see here, there are very nice tutorial of this about this plugin in the YouTube. You can find it. As to the implementation, okay, I'm going a bit faster. Our research strategy, as you know, this is very typical top-down and based, you know, bottom-up approach in the computational and digital fabrication. And what we are doing is so the somehow bottom-up. This is very interesting with connectors by developed by the XFix, you know, company. You can have put their resource here. You can find information about it. It's very interesting. We use this kind of, you know, connectors to produce more complex structured timber shells, and you can see the timber dome is it's a prototype present a completely prefabricated, easy to use assemble solution entirely made from wood. Very strong, lightweight, and highly, you know, sustainable building. With this actually based on the XFix system, you know, and just, you know, very easy and fast to be assembled. And you can see here the process, okay, and here the detail about the XFix connectors. we use this system, actually, because you see the the precision of this cutout is really interesting, I put it. We use the system, as I mentioned, to type this timber dome. It's kind of, the prototype test model. Actually, it has been presented at different exhibitions. You can find the information easily. And I would love to mention this interesting project, Recycle Shell, which is, absolutely similar to this, to the previous one. But it's, worth mentioning that, I have to say, instead of presenting the project, it's very important to present the system that we are practicing, so this system of algorithmically generated CAD model, you can see it has the same strategy, same approach, but with different shape. You can see this here. It's okay. Now you see this is the direct, fully automated transition of the data to the to the machine. And here it is pretty simply an assembly inside, which is very quick. I will share the relevant links so you can find the information, details about this, the dimension, there are many details about this, so you can find all this information later. And here is about, I put some videos to be, since, okay, this point. Okay. Here you see the assembly of the whole project. Very fast, and so it has been loaded. Actually, the DTC, as I mentioned, there are different, researchers with different area of research. So, so for the structural part, you can send an email directly to the tier support. So, and at the end of the project, you can see here, it's been kind of, giving group. But actually, I don't know, the connection is okay.
Okay.
This is, time. Can you hear me?
Yeah, we can hear you. Are you finished with the presentation or?
No. Just
okay.
I'm very faster. Here, the data, as I said, it's a strategy, but very, in a faster way. Here, the information is the movie about it. Thanks to this huge, let's say, CNC machine, also, integration of different customized software. We're able to produce very interesting, and also the next the next one here is this assembly. The last one was about the production of the glue, and also the cutting the milling the shell. And here you see how easy you can. This is it is cut. So you can find the full movie. I will share all this links later. You can see the full movie, and it's really easy to assemble. And also the button, you can see the precision also is really interesting. Okay, and just quickly talking about the another one, another prototype. It has the same strategy. It's top down, bottom up, and also we have worked on the joints as similar to the previous one, but it has different strategy, different type of connectors. So you can see here the details of the read-only wedge connector, but it's of the joining system. And here it's a first version prototype of wedge connector. You can see also the axonometric of it. Here's some running, and also on the right you can see how it works, and here's some details. It's the first version for solid wedge connector, so very interesting. And here you can see, if I want it steps, how it is made. Actually, the project was done by the DTC, a nice collaboration between the DTC and Cote Production and the University of Sydney. And here you can see the assembly. This is a very nice prototype developed by our student assistant Enrico Valentino, which is very nice. It has been done at the TU Kaiserslautern, before the assembly of the one-to-one scale. Well, of course, it's one-to-one, but not the whole project. But it's very interesting. It shows that how we are practicing at DTC. Here it's a manufacturing process developed by Cote Production team, also the AF technicians at the University of Sydney. So it has here you can see it doesn't matter if it has been it's made by the robots or CSK. So we can use both of them thanks to the plugin that TPS plugin, which we use. And also here some photos from the drilling and installation process and the boxes assembly. Also you can find the thesis of Enrico Valentino, which is very interesting. There are many information about the details of this publication process. And here, expected to the final, you can see our colleagues. Christopher is there, Valentino is there, and also it's very interesting to see how they are assembling. And many of our workshops, actually this is the previous workshop developed by DTC at the University of Sydney, but many of our workshops are at the University of Queensland, and many other universities have been postponed due to this critical situation. And about the contract, as I mentioned, you can find all this information at the Digital Twin Reconstruction DTC, and also they can ask any question or curiosities. You can share your curiosities with me or Professor Christopher Roper. And the whole information here I have mentioned, as I mentioned in the beginning, the foundation of what we're practicing here. So the joints, the automation, using CNC machines, creating sort of data interface to translate all this information from the computational model. Rather than computerization, we are focusing on real computation, to translate all this information to create a sort of interface, and which machine can learn easily, and it's all under the radical of the let's say automation. And thank you so much for your time.
Thank you very much, Amin.
I am open to the discussion, but that's why I try to move forward very fast. So I will discuss later.
Okay. Thank you very much, Amin. It's really interesting work. There are several universities working on digital design and fabrication of wood, and for sure, TU Kaiserslautern is one of the pioneering universities in this field. We move directly to the next presenters. I'm sure there are some questions, and I would also like to invite the presenters to be a bit faster for the presentation, so we would have enough time during the discussion. So Farzaneh, you may share your screen.
Yes, sure. Let me share. Can you see my screen and hear me well?
Yep.
Okay. Hello, everyone. My name is Farzaneh Eskandari.
Can you? Yeah.
Yes. Let me. Okay. My name is Farzaneh Eskandari. I'm an alum of University of Tehran, Iran. I majored in architectural technology with a focus on computational design and digital fabrication. Recently, I've been working as a digital fabrication tutor at our university. And today I'm gonna share the result of our recent project as digital design and robotic assembly of a timber structure. The workshop was carried out under the supervision of Dr. Mohammad Reza Matini and was tutored by 3 of my colleagues, Mehran Masoudi, Sayed Ali Derazgisu, Ramtin Haqnazar, and me. On behalf of our team, I would like to say thank firstly to DigitalFUTURES World for providing this great opportunity for us young researchers to share our projects and research worldwide. And I would also like to welcome every audiences who are watching this session online. Actually, our workshop this workshop held by the collaboration between SIT as Center of Excellence in Architectural Technology at University of Tehran and also DCH as Digital Craft House Lab in University of Art. My 3 colleagues as members of DC House Lab and I as a member of SIT have been working on the computational design and digital fabrication for several years, and the idea of using robots in the construction process of our project came to our mind when we encountered some difficulties during the assembly and installation process of our previous works, like the ones you could see in the bottom of the screen, which were mainly carried out by DC House members. Anyway, in this wise, we decided to hold a workshop to explore the potentials of robots application in the construction of a timber structure in an attempt to increase the ease of installation, decrease the time of fabrication process, and enhance the construction accuracy. This 10-day workshop was attended with more than 30 graduate and undergraduate students from various universities around Iran. I would like to say thank to all of them for their great collaboration and tremendous teamwork they performed. We planned to carry out this workshop in 2 main parts. And in the first part, the students conducted some two very basic exercise to learn about the concept of path in robotic simulation. And in the second part, the students was tutored to design a timber pavilion to be constructed by the robots. As their first exercise, each group was asked to generate some G codes to define the motion path of the robot, and they ended up generating some interesting 3D light paintings. And for their second exercise, each group was tasked with designing some very simple structures with only a limited number of wooden elements to learn about the pick and place technique, which could be used in our assembly process. And you can see here some of the works of each group. After performing the introductory tasks by the students and getting acquaintance with the practical and technical challenges, each group of students embarked on designing a timber pavilion in a scale of 1:1. And here you can see one of their projects, which was selected to be assembled for the final construction. Due to the time limitation, I didn't put all of the group's projects, and this is just the selected one. There were some major limitations that should be considered in the design process of our project. And the first one was about the amount of available material we had, which was about 40 square meter of 18mm plywood. And the second limitation we had was about the maximum reach of the robot's arm, as we used KR6 robot, KUKA KR6 robot, which had a maximum reach of 1.5 meter. So given this limitation, we had to halve the designed arc, and each half was split in 4 and you could see here in this part 4 and 5 sections to be assembled by the robot based on the robot's reach. And finally, we had 9 sections of wooden elements that were assembled by our robots. And you can see here the robotic simulation analysis. For the connection of our wooden elements, we proposed 2 methods for the construction. As our first option, we used a glued roller here, as you can see in the middle of the screen, to which each part of each wooden parts would be rubbed by the robot and then be placed in their position. And as you can see here, the robot would first pick the elements and then rub them on the glued roller and then place them in their position. However, due to some limitations we had, like the material we used for the glue didn't dry enough fast. So in some regions, like in some elements in some regions, like here, the elements which had lower common area with their bottom elements needed something to stabilize them temporarily until the glue dried. So we performed a second method, a collaborative human robotic method, by which someone would use a pneumatic nail gun and fasten the elements after they being placed by the robots. And as you can see here, we used this collaborative human robotic technique. Yeah. And after all the 9 sections were assembled by the robots, they were transferred to the campus of our university and installed by students in less than 2 hours. Okay, before going to the conclusion, I would like to introduce 2 other achievements of our workshop, which in my point of view were very important. The first one was this. Let me mute the music. Okay, the first one was this I/O device, which we designed and built ourselves. You know, when this robot was transferred to our university, we realized that it didn't have an I/O device for generating the digital output. So we didn't have enough time to provide one. So we decided to design and build one ourselves. And by using some very simple tools like a microcontroller and Sheth encoder, we built this this box here, which could convert the rotation motion of the robot into some digital output for us, for closing and opening the pneumatic gripper, which we used as our tool for this robot. And the second one, which I mentioned, was this very precise algorithm and a program which was developed during the workshop. And this algorithm gives us the possibility for generating the robotic simulation as precise as other softwares which are used for robotic simulation, like KUKA PRC or other plugins. And I would like to say thank to our friend Dr. Alireza Fazal for generating this, for helping us to build this I/O device, and our colleague Mehran for his great work to develop this algorithm. And finally, I would say that we planned this workshop to practice the using of robots in architectural construction. And using robots in architectural construction could enrich the designs. Could enrich the designs of architects by providing the possibility to build more complex structures with more considerable accuracy in a lower period of time, and moreover with a fewer number of manpower, and especially in the time of this pandemic, which we have been struggling with during this month. I think it's a requirement, it's a basic requirement that, in my point of view, need to be considered in architectural construction processes. Thank you all for your time. If you have any further question, you can refer to our websites, or you can directly get in touch with me via my email.
Thank you very much, Farzaneh. I'm sure we come back to this in order to keep up the time a bit, which we are running behind. We directly go to the next presenters. Can you share your screen, Bhavleen?
Yes.
She's joining us from Mumbai, and please share your screen and start. Thank you.
Yeah. Hello everyone, my name is Bhavleen Narula. I'm currently teaching as assistant professor in Balwant School of Architecture. I'm here to present some of the work done at Studio Samipadora and Associates. Squaring the Circle is an architectural installation and was created as part of an exhibition Venice Space held in 2018 at Jawahar Kala Kendra in Jaipur, India. The exhibition was created by Mumbai-based architects Rupali Gupte and Prasad Shetty. As part of the curatorial framework, the installation looks at the idea of mathematics of the universe, interrogating ways in which mathematical logic is employed to reinvent form and space. The installation was made with Elastane Fabric, commercially also known as spandex or lycra. The fabric was stitched together to form catenoidal surfaces to occupy the gallery space. The presentation, Digital to Production, looks at this installation as a reflection on the question of methods and fabrication processes involved in a digitally computerized model. The provocation for the design and formal exploration came from two coordinates. First was the curatorial provocation, where the curators of the exhibition wanted us to explore the questions of mathematics of the universe. Second was from the double height circular gallery space that was allocated for the installation. The section of the gallery was created by two intersecting forms, a circular slab and an intersecting elliptical mezzanine floor. The ellipse created an interesting challenge in the development of the catenoid form, as it created a shift in the axis of the form. We decided to add a third shape in the section of the gallery, a square form on the floor. The resulting catenoid form was a mesh that morphed from a circular roof to an off-centered square frame on the floor, while carefully negotiating the shift in the axis introduced by the elliptical mezzanine floor. While experience the form from within, it further extends outwards as a portal from the adjoining landscape on one side and another gallery on the other side. In order to connect the two planes as shown in the design development stage, multiple iterations were carried out at the studio. The prototype shown here broadly uses three materials for analog experiments. The non-elastic net used in the first case did not show any mesh relaxation under any given tensile forces, whereas the woolen threads upon revolving around the axis formed hyperbolites. Experiments with Elastane Fabric, on the other hand, resulted in minimal surface catenoid, as seen in a typical soap film experiment. The Elastane Fabric accommodated the tensile forces and gave more degrees of freedom to stretch in multiple directions. Naturally, the Elastane Fabric was a much better choice for the installation. At prototype scale, the fabric was cut into strips and stitched together with non-elastic thread. Besides longitudinal seams, additional seams along the latitudinal direction provided reinforcement to hold the fabric in place. The prototype informed us that the Elastane fabric could stretch more than twice in length. However, at the same time, it would shrink by 10 to 15% in width. The material studies were also conducted at site at 1:1 scale with longer continuous pieces of fabric. We noticed that any piece that was stretched more than 1.75 times its length led to tearing of the materials around the seams. Several form conditions of the installations were also tested at 1:1 scale to check the material properties. To figure out details of the anchoring of the fabric without wear and tear, and test ways of stretching the panels of the fabric with one another such that the seams can sustain tensile forces of the form. Due to this property of the material to be able to stretch almost 1.75 times its size, the installation was done in 320 square meters of fabric material than its actual 426 square meter of area that was shown in the computer generated model. While the project was designed and understood in a more digital environment, the fabrication process needed better understanding of the fabric, appropriate tools and craftsmanship. The team of tailors who crafted the space for the final installation were expert in making curtains, upholstery fabric for the furniture, and they were then also much skilled in understanding the complex geometries of the prototype at 1:100 scale. But also, they not only just were able to understand that, they also suggested better material, color, better dyeing techniques for the fabric, and also understand the forces acting on the parts of the installation at the actual scale. Even though the prototype and the drawings extrapolate the making process as derived from the digital codes, the fabrication logic remained entirely with its craftsman, his material knowledge, and the craft of his team. The assembly workflow was done in 3 stages. The framework, which you see at the bottom, the dyeing, cutting, and stitching of the fabric, which was done separately, and installation of the panels on the hook was the last stage. J hooks were welded on the MS framework, defining the bottom framework of the installation, and anchor bolts were drilled directly onto the wall for the top parts of the fabric. For the ease of the workflow, the installation was broadly divided into 4 sections of cutting and stitching of the fabric, which was then put together as you can see in the next images. The panel drawings were made for each part, which was then used as template for marking and cutting out the fabric. Keeping material wastage in mind, panels were arranged to get optimized size. Any material from the cutout parts which was not used was taken carefully aside and was used for much smaller parts. The final installation, if you see in the slide, required the whole marking, cutting, and stitching process, which was carried out in around 220 hours over a period of 22 days, and with a team of 3 tailors and 1 sewing machine. The installation was done in 2 parts, finishing up the first half with the top anchor points and then stitching the bottom points with the onto the MS framework at the bottom. The entry and the exit points were hooked at the end. The entire process of installation of bringing the fabric onto the hooks took less than 6 hours. The installation also during the process of installation, the material behaviors were quite interesting. The video over here shows a bit of behavior with the kind of tension that the material could have. It had to be pulled strongly to the bottom half to connect it back to the anchors. And in that whole process, it could also lift up a 300 kg MS framework, which was then put with counterweights at the bottom. So these are just some images from the final installation and the kind of forms that were generated by the fabric. And the gallery space above the mezzanine level kind of looks at this huge and wide spread of fabric. Over a period of time, towards the end of the installation and towards the end of the exhibition, and over a period of 5 months, there were very light changes into the parts of the installations which were more exposed to the sunlight and more exposed to the wind. But otherwise, there was hardly any change. And in the similar way, the whole uninstalling process was done in around 2 hours time. It just had to be unhooked and transported. Yes.
Thank you very much, Bhavleen. Really interesting project bringing craft and computation, both digital and physical computation. I'm sure that we come back to this project.
Yes.
Thanks for also taking the time. So we move to the next presentation by Adib, who is joining us from the South Institute of Architecture, where he is also a tutor at DARS, Design, Architectural, Robotic and Systems Studio. So floor is yours, Adib. Please go on.
Can you hear me?
Yeah.
Okay, hello everyone, and thanks for this great opportunity. What I'm about to show you is the result of my architectural thesis project in DIA and the South DARS Lab. And my professors were Sina Mustafavi from DARS Lab and Manuel Kretzer from Materiality. So we know how transportation is an integral part of the history, but we can actually see how it developed and relocated cultures throughout the world. And in this timeline diagram, you can see how the Industrial Revolution changed our transportation means from engine chips in 1769 to tunnel fast train in 1995. But the good news is we're going to have the first Hyperloop line in 2022. So what is Hyperloop? I can give you an example so you can understand what is the difference between this and the other means of transportation. So if you want to go from Berlin to Paris, for example, it takes around 4 hours for the fastest means of transportation, which is in this case a plane. But if you want to go with Hyperloop, it's going to take only 1 hour. But the energy consumption of the plane is going to be 515 kilowatt per person per kilometer. But for the Hyperloop, it's going to be only 14. So the Hyperloop story, when people hear about Hyperloop's name, they directly think about SpaceX and Elon Musk, but I'm thinking he's the owner of the whole Hyperloop system. But in fact, the physical concept of the Hyperloop was invented in the 19th century and developed during time. Actually, in 2013, Elon Musk published a white paper about it. And from now, from then till now, it's being developed by the other companies. So I'm just gonna tell you how it works very fast. So it depends on the technology of the company, but mainly it has 4 different characteristics. It has electromagnetic suspension that elevates the unit inside these tubes. It has the low pressure environment that vacuums almost all the air from it, so there is no fraction. And there is this electric repulsion which moves the pods inside these tubes, which they can go up to 1,000 kilometers per hour. And the Hyperloop switch, which makes it autonomous, so there is no need for any more pilots. And the infrastructure is also important. It can be above and the ground. It can be integrated to the existing infrastructure, so there is no need for occupying another lands. So we can use also the solar panels on top of the tubes, and it's the on and off ramps of it. It's exactly like the on and off ramps of the normal highways. So, and here you can see how what MAD Architects was developing for the Hyperloop TT in Abu Dhabi, in Dubai. For the design methodology for the main part of my project, I was thinking about the symbiosis of discrete and continuous materiality. So we know that being discrete or continuous in design to materiality has been recently celebrated among the architectural discourses. As Gilles Stretsin or Mario Karp was talking about, with discrete approach, the contrast between the virtual and the physical reality becomes very smaller, because we're designing in the digital environment and then we're building in the reality, but we have to design also, we have to also build digitally, which means we have to build by the bits. So the methods of the process and the design fabrication and assembly becomes more streamlined, although critics are not convinced by this habitability of this discrete approach towards architecture in many cases, such as the statics of the materials and being safe while facing natural disaster, and also the restriction of having one unit as block and building merely from it will decrease the degree of freedom in morphology of the space. So I decided to include both of this method in my equation and create a system that accommodates both of them beside each other, and use them separately in certain part of the project and explore the clash and blend between them. So from now on, I'm going to talk about 2 parts of my project, discrete part and the continuous part, and I'm going to see how can I merge them together in one system. So for the continuous part, I was thinking about the extreme condition of being continuous and discrete. In the continuous part, I was looking into different smoothing algorithms to create complex double curvature geometries, which is possible through continuous fabrication techniques such as large-scale 3D printing, contour crafting, or prefabricated mold casting. So I decided to assign them to the static part of the project and mainly the envelope of the station. So this is going to be my continuous part. And as you can see, in order to control the continuous part, I had 3 different parameters to work with: the polygonal subdivision, the edge subdivision, and also the breach size between them, so I can connect 2 different geometries very smoothly. And for the discrete part, in the discrete part, they are assigned to the we have motions and dynamic movements in the project. So I was looking into velocity field and the particle system simulations to create advected motion of them, resulting into linear discrete geometries derived by the forces and vector fields. So in this case, I was controlling the frequency amplitude at time, since it's a recursive algorithm. But still, it wasn't discretized. So I was thinking, how can I control it? And I realized if I can round up my vectors, and I can have the same effect, but more materialized. So in this one, you can see I can have 3D printed elements and then assemble them together, or I can have bended road elements robotically, volumetric elements and then bend them, or folded strap elements. After that, the site was also super important in my project. So I was thinking about going to Germany and picking the site in Berlin, because Berlin is very important in terms of being a hub for transportation towards in Europe in general. So Berlin air passenger traffic is 34.7 million per year. So I had to pick myself somehow between these two airports that Berlin has. And also the railways traffic is really important in Berlin. So for example, in 2018, S-Bahn, which is one of the metro stations of the Berlin, only moved 4,017,000 passengers. So I had to also be adjacent to the main rings of the S-Bahn. So, and that's why I picked Tempelhof, which is exactly between these two airports, and it's adjacent to the main ring. And history, also Tempelhof has its own history. After the World War II, it played a very important role for Berliners, and it's a place for airlifts, which is where packages of food and goods was bringing to the people in the airport. So it's somehow emotional for the Berliners. And in 2008, 59 years after the airlifts, the aviation activity came to an end in Tempelhof. And then the city decided to sell it to the real estate and developers. But people couldn't bear this decision and started some campaign about Tempelhof. And in 2014, they decided to, and assured that there will be no more further development for the private developers. But I assume that the part of the Tempelhof can be still served as a transportation hub for the city. And you can see how the site is very, very big in the middle of the Berlin. I'm going to use only this part of it. And here you can see the main road of it, and the S-Bahn is coming from here, and the main pedestrian walks from the site. And these are the vectors that I'm going to use later to create my system. For the design process, I started with modeling itself because the project is completely unknown. There is no studies that I can learn from. And I had to create something and then criticize myself to achieve the best proportion, program, and even the form. So in order to engage people on site to the project, I wanted to have big semi-public space in the floor ground and to maximize the light radiation, at the same time maximizing the platform areas while having the minimum tubeless inside the main hall. And here was the result. So I'm going to have this big hall, which is hollow in the center, as a negative space in the center. And for the functions, I had hotel and offices, retails, pod station, and lobby and platforms as the main function. And I had the different layouts, how can I combine them together. And this was the last one that I picked. So this is the hotel and retails, and the pod retail goes all the way on top of the lobby and platforms. And here's going to be the station and platforms. And for the design process, I started with abstract volume and bounding boxes to work with. And then I gave these bounding boxes the function that I required for the project, which is the hotel office, retails, and the platform station and the lobbies. And I exactly knew the elevation of in and out Hyperloop tubes inside the building. So I created levels with the specific heights inside these bounding boxes. And since I have explored the platform layout in order to maximize the light for each level, and also in the center of the building, and also having light for all of the rooms in the hotel room, I ran the light optimization, and this was the result of it. So here you can see the abstract version of the continuous part after the light optimization. For example, the hotels now, there are two. Before that, they were like a big chunk. And after that, from this abstraction, I ran another multi-objective optimization, but this time on volumes to maximize the light and tune the architectural needs of the project. Having the volumes, I could code them and create a simple envelope of the building, which was ready to be smoothened by the algorithm that I was working with before. And here you can see how it was changing and being smoothened and also a bit shrinked. And this resulted to surface subdivision. This is a result of the surface subdivision that you can see. And here, from now on, I'm gonna assign this the continuous part and work with the discrete parts after that. So having this continuous part, I could run my particle simulation to create a discrete part. So I created the point cloud around the building and started to recognize my internal and external forces that were forming my velocity field. For example, I had two vortexes here because of the entrance of the pods, the pedestrian in here, the S-Bahn in the below, and the retail entrance in the here, and all of them are forming a velocity field for me. In here, you can see how it's moving when we have the particles, and then by recording the behavior of the particle system through time, I could create a linear fog of discrete parts around the building, which was completely derived from the internal and external forces of the building and the site. And I used a similar method for the site point cloud that was also informed by the movement of the pedestrians and the different in and outs of the building. For example, the main pass, the South Tempelhof pass, the pods in and out, S-Bahn, and the North Tempelhof pass. And here was the result of the particle system that was driven by those forces. So now I had this aggregation of discrete fields around the building, and it was the time to select the parts of it and see its reaction towards the continuous part. So having the levels of the building and functions field was selected, this discrete field was selected from the parts that we have the most motions in. For instance, the movement of the Hyperloop pods inside the station, the movement of the passenger, the hotel user, the S-Bahn entrance below the building, and so on and so forth. And having that selected field, I ran the particle system simulation once more to see how they react in this space now, in the selected field part. And then this resulted to a recorded behavior of this particle, but it wasn't enough yet. This discrete part is only penetrating the continuous level, and we couldn't see the reaction between them yet. And that's why I started to select distance-based areas of the continuous part and added a physical force to their skin and merged these two fields mathematically. So now the discrete part was not only going inside the continuous part, but also being distributed on the skin, informed by the physical clash of these two different morphologies together. And here in this video, you can see how these two fields are merging, and then the left picture is the first result of the simulation. Here you can have a better look at the combined velocities and how it's merged after the 80th iteration. So that the bluer it is, the smaller it is, and the purple ones are the longer velocity fields, advected velocity fields. And the last part of the discrete part was the structure of it. I needed a structure that holds this and supports this field together. So I applied this branch structure that could tighten up the discrete part, and at the same time, this intersection between the discrete and continuous. So here you can see how it's being developed, the branch structure. So to summarize the system behind this new level of tectonic that is created by the clashing and blending of discrete and continuous, we have the movement of the flow discrete is here, and the collision discrete that we have in here, the continuous surface, and also the structure that holds them together, and also it's between the intersection of them. And here you can see how it looks from the other way. From the top, and slowly I started to add a new level of tectonic to the continuous parts also, because definitely we can't have a contour crafting or like a large 3D printing scale in this scale, because we definitely had to assemble some of the parts. So I had these seams that you can see, and there are some documents, but I think we don't have time to discuss them, but you can see like how the tubes are penetrating in the continuous part, and here they go out and they come back again, and the platforms. Here are some renders that I'm gonna share with you. Here how it looks from the back. And I'm gonna show you a short video about the project. Thank you for your attention.
Thanks, Adib. I'm sure we're going to come back to this presentation. While you were using the term discrete and continuous many times, we have really interesting discussions going on in the chat. Also, a very interesting paper by Neil Leach called "There's No Such a Thing as Digital Building: a Critique of Discrete." I think we're going to definitely come back to this terminology and presentation. So, but to finish today's presentations, we would move to the last presentation by Bartlett School of Architecture, a group of 4. So please start.
Hello, we are Georgia, Barış, Ella, and Ife, and we are a team of postgraduate students from Bartlett from Research Cluster 3, Living Architecture Lab, and we will present you a project about an integrated configuration system in living architecture. As a studio, we are focusing our research in exploring the notion of living architecture and breaking the linear life cycle of conventional architecture production. In this direction, these following projects had been used as our inspiration precedents as they have tried to introduce adaptability in the buildings. Our proposed system, Ursula, is an autonomous architecture machine capable of adapting itself to negotiate the needs of a near-future cultural center. The design process is shared between the algorithm, the user, and the architect, while the building physically reconfigures through a multi-agent robotic system that inhabits it and its library of simple connectable parts. Starting from the bigger scale, we first have the algorithm that creates different designs for the space. Our algorithm puts together different tiles that are being voxelized by various smaller components. And last, we have our bespoke multi-agent robotic system that is responsible for the assembly of these small voxels. So in order to present your project, now we're going to reverse the process and start from the smaller scale of work, which is our robotic system. Our algorithm
For the robotic system, the main goal is to design a multi-agent system to achieve the reconfiguration of the architecture. At the beginning, we tried to apply this robotic system with different functionalities and abilities. For example, we used OptiTrack to help the robot track the target and moves toward the target. We also tried different kinds of locking system and walking system, which makes our robot has more and more degree of freedoms. So we realized that we should simplify the system and design it more specific to our components. Then we have our new collaborative robotic system, Coco Robot. This robot with a scale of 50 centimeters has only 3D ground freedoms, but it has the ability to climb the components in 3D space and move the components horizontally, vertically, and diagonally. For the design of the robotic body, we simulate the body with different materials in different loading conditions to try to have a more generative design to make it has the minimal weight, at the same time bear more loads. Finally, we choose carbon fiber as the material for 3D printing. We use electric magnets as the locking system so that the robot has the ability to climb and also grab the voxel and release it. Next are the demos we made for this new robot. The first demo shows how the robot can walk on the components in X, Y, and Z axis. Unity here is used as the interface where users can give the target position, and then it will automatically calculate the robotic movements and provide feedbacks to control the robotic prototype. The second prototype shows how the robot can rearrange the components in X, Y, and Z axis and to achieve the reconfiguration. Machine learning is used to train the robotic movements. After training, the robot can always reach the target in the fastest way without touching the barrier, and can also work in different arrangement of components, and also know how to walk independently in 3D spaces. After that, two agents are trained at the same time to make them have the ability to cooperate with each other and move the components to the target position without changing the orientation. With the training result, we designed another interface in Unity as the controlling system. Here, we can choose how many agents we want to have and which shape of small tiles we want them to build up. Then the Unity will automatically show the result and use it as signals to control the prototype. From this interface, we can find the more agents, the more efficient the system works. And then we use this interface to control the prototype with multiple agents. In this video, two agents can not only work independently, but also have the ability to cooperate with each other to achieve more abilities. For example, one agent can pass the voxel to the other, and also they can cooperate with each other to fix the orientation of the components. Next, we will introduce our design of the spatial units.
The spatial units that will be later put together by the algorithm are being voxelized by using small components, so they can be assembled by the robots. And the scale of robots and components adjusted in optimum size that components can also be carried by robots. The spatial units created from 3 classes of tiles in according to truncated octahedron geometry grid, and we extended the variation of it based on their connectivity. By analyzing several aspects of units, we are setting properties to be used in the algorithmic generation process. For example, with the force analysis algorithm, we evaluate the stability of the units. Here is one outcome of spatial tiles assembly that we voxelize it based on the cross components. In addition, we consider different levels of transparency of same typology of components with a variety in material to achieve different results of materialization in interior and exterior spaces. For example, ETFE components work as a transparent components, and some of them have better functionality in load bearing of the structure.
Okay, our algorithmic design process works in 2 different scales: subscale assembly and overscale planning. Planning algorithm selects which tile class will be used for the node, while assembly algorithm selects the tile from the class and places it. So first, we will start with the subscale. Assembly algorithm is a constraint-based system that connects elements according to the connections that they can make. Using truncated octahedrons, several surfaces in this connectivity-based process makes it possible for IRSLA to form complex spaces. In Ursula's space creation process, there are several layers of control. The user control lets users to place starting nodes in shape of vertical circulation, mask specific areas, or trigger manual reconfigurations. Users can also change the importance of tile properties and the footprint of the building to achieve different outcomes. Ursula's role in the process is not only generating, but also refining the outcome. By running simulations based on stability, crowd behavior, and connectivity, it can keep evolving and improving itself. These processes continue even after it is built, as it starts using sensory data, which makes Ursula a continuously evolving and adapting living system. We are further improving this evolution process by implementing reinforcement learning and training algorithms to score every tile dynamically, which makes it possible to eliminate extreme cases and get better outcomes. These several layers form the assembly mechanism of Ursula, but as we have said at the beginning, there is another level of constraints on top of all these layers, and that is the spatial planning. The spatial planner is creating agents with colors, and these agents influence their neighborhood tiles by slowly filling them with their color pheromones. Then they move to the next tile that has the pheromone color closest to them. We are using these behaviors to deconstruct conventional cultural center spaces and reconfigure them by relating different spaces to different agents. As clustering itself is not enough to define architectural spaces, algorithm is trained by setting goals based on spatial needs and giving a certain degree of control to agents with machine learning. These agents act like the inhabitants of our grid environment and use the nodes as resources they can occupy. Later in the research, it will be possible to try different behaviors in this architectural terrarium, but currently they are trained to act in a mutualist relation by benefiting each other. Yet, even this is enough to adapt to several scenarios and guide Ursula's assembly sequence, as you can see here. So now let's take a final look at Ursula's face generation and reconfiguration process in several scales, starting with algorithmic scale. Then voxelizing one of the algorithmic outcomes, and reconfiguring the voxelized space.
Thank you.
Thank you. Thanks for listening.
Thank you very much. Really interesting projects. So it's good that we have finished more or less on time, so we have enough time for discussions. If you stop sharing your screen, then we would directly continue with the discussion. Yeah, great. Okay, really interesting lineup of presentations. I'm sure there are a lot of questions. So we would directly start maybe from the committee and organizers, if there is any point to start with.
Maybe I could just, Sina, since you kind of commented on I just put an article on the chat about the discrete. I don't know. I just despair when I keep hearing this discussion of the discrete. I mean, the world is made up of discrete components and continuous components, and it depends on how you zoom in and zoom out. Even the world itself can be seen as a discrete entity when you go zoom out far enough. And I just see it as a kind of rather, I don't know. For me, it's just the kind of stylistic thing that's come about. After Patrick Schumacher was arguing for the linear, we get something coming out largely from the Bartlett about the discrete. And actually the world is made of both, as indeed the Dessau student showed in some ways. And I also think that we need to also think in terms of it's individual entities, but also seen as kind of I don't think we can divide the world into discrete elemental way of things. Anyway, that's just my viewpoint, but I'm surprised it's caught on, this discourse, so much everywhere.
Okay. Any reflection?
I remember Gilles Reston reflections on the discrete idea with Philippe Bloch on Digital Futures in Shanghai 2019, if you remember. Yeah.
No, exactly, exactly. I mean, Philippe and Jules both come from Belgium, so they had an interesting discussion about you. You don't in the discrete their load, right? That you can't see them as discrete entities. Anyway,
maybe go on.
Okay,
please.
okay. No, I want to say something that I believe that, as Manuel de Lande said, that there is not two types, the continuous or the discrete. But anyway, I think that maybe we made a mistake, architects, we made a mistake when we try to put organizational structures of building processes and we try to put it in physical forms. I think that maybe that's our most difficult part. We try to do it a lot of times, and I think that's the problem. We already discussed this in other sessions, but I think that maybe this is something that we can discuss, how we try to put some concepts or things in physical form, because there is a lot of problems. Also, I think that maybe we are stuck in the way how we think assemblages. Because I could see in all the designs that you presented that there is some issues with assemblages, not only assemblages in the matter of, in terms of matter, assemblages between different materials, because today we can say that we have a kind of, I don't know, of a presentation which were about wood. We can say that today was the timber day because we have many of these presentations in good. But anyway, what I see is that there is not any problem. We are not thinking about the assemblages in terms not only between pieces of wood, but always also about complex social assemblages and cultural and economical and geographical assemblage. So that's
Great.
only
Exactly.
our reflection.
Yeah, and I think one of the problems comes when we start to tag the whole idea or phenomena of architecture. When we call discrete architecture or digital architecture, I think this is a bit misleading. While we can think of discretization or digitizing in architectural design, but when we introduce it as a kind of even if you think of parametric architecture, I don't think there's such a thing as parametric architecture as a style. You can think of parametrization or parametric design, but architecture as a phenomena, I think, cannot be reduced into something like discrete architecture. But at the same time, I think it is also really interesting that while we are moving towards the robotic fabrication session, many of the projects here are addressing this idea of assembly that you also mentioned. Maybe our presenters have some more words to say about this assembly.
I remember 10 years ago, there was a competition called Shelter Competition. I remember that the winner designed some kind of discrete, but he didn't mention it is a discrete, but he was thinking of a long element that can be assembled by the users. So the idea was do it yourself. If you want a shelter, this is the elements and just do it yourself. If we look for the discrete element from this approach, I think it's fine. But in a mega structures, we have some questions.
Yeah, maybe we can start with Jan, the first presenter. So you had this idea of assembly of elements and units in a large scale, but at the same time, it was really interesting to see that you are sort of criticizing this way of looking into architecture. The way, for instance, at least Koolhaas was looking into architectural elements in Venice Biennale, sort of dividing the elements of architecture into stairs, column, etc. While the approach that we see in many of the projects today are questioning this way of formalizing or looking into the architecture. How do you see the role of computation when it comes to this basically basic elements or fundamental elements of architecture?
Thank you for the question. It's actually one of the more complicated ones. I must say I agree with what has been said before, that if we think, for example, about parametrics in architecture, even the whole idea of computational in architecture, I think to a certain extent there are labels that we also, researchers, architects, we use anyways, because we need some simple way how to categorize and label what we're doing, be it as it may. So with my project in the beginning, I was also somehow intrigued by the idea of discrete, as many people here, and as it was criticized. But at the same time, I believe that there's a bit more to basically the idea of assemblages and of assembly and of using pieces only as some sort of units. And that being said, maybe coming back more to your question, I was quite interested in hybridization of archetypes. So basically what Kováříček presented at the Biennale and with the huge book that they produced. I think it's somehow a shame not to look beyond, and that for me maybe is the nice idea of the computational tools that we have. It doesn't have to be necessarily parametric architecture, or it doesn't have to be, I don't necessarily need to use swarm behaviors or something just for sakes of using some sort of a more or less advanced simulation, right? But for me, it's just really even understanding a traditional technique, such was me studying and trying to understand carpentry joinery, and try to rethink it in a different scale. So upscale it to, let's say, the archetype scale, into scale of, how a simple detail could be upscaled into architecture, and can I use that to, as I was saying, hybridize the elements? So can a staircase could be also a part niche. And actually, I think I came up with this idea when I was looking into the discrete architecture. And for me, it was weird that all the projects, which in my personal opinion are quite beautiful, that work with discrete, they don't really speculate on the types of spaces and the types of, again, elements or archetypes they recreate, right? So you can still distinguish the building unit, the block, basically the new brick. And the other part of why I decided to go in that direction is, and again, to be a bit critical towards the discrete, is that to my understanding, there is a, let's say, defense of a discrete in the scope of, okay, we have, let's say, 12 versions of a new element, a new brick, and that brick is standardized. It is more advanced, it has certain features, certain different qualities, but it doesn't, it's still kind of like a standardized element, which I personally saw as a big, let's say, contradiction. If you think about robotics and CNC manufacturing technology, we don't need to, in my opinion, we don't need to create standardized building elements. So therefore, yeah, I focused on creating non-standardized pieces, which would be compatible with each other through the joining, but not through their shape itself.
And one question: to which extent this non-standardization of components were done computationally or in an automatic way, and to which extent manually? This is, I think, one of the main challenges when it comes to assembly, being able to fully compute in an automated way this idea of assembly. With the level of complexity that you're showing in your project, I think it's a very tricky thing. So maybe you just can have a short answer. To which extent this is done manually, and to which extent this is done basically with your own intelligence, and to which extent with some sort of computational intelligence.
Right. So, well, if we would define a computational intelligence as something that there's this working script. I remember your first computational, that was 2 weeks ago, the first collection of lectures there. I think there was a researcher from Japan that worked out a system that generates exactly these Japanese joints, which was quite incredible. But for me, so I was using my knowledge of the joinery, of the carpentry, but at the same time, for example, I was working with tools such as Maya and a bit more advanced animation techniques, because it was not only about, well, it was about the assembly. So I had to figure out the step-by-step, how you can interlock each piece to one another, which eventually got quite complicated. So I didn't see any kind of a, let's say, in the time scope of 3 months that this project was being created, I didn't see any way out how to automate that. So in that sense, it was not automated. It was, but again, I think we can argue, or we can discuss how do we think of what do we think of computational architecture in general, what it is defined. So I was using computational tools, but I was using it as a designer, in a way, maybe as a digital craftsman, trying to figure out the geometry itself.
Great.
Maybe Sin, I could pick up on that. I mean, what's interesting to my mind is the way that we have a kind of like, actually the categories themselves are not discrete, right? Because we're now dealing with computational design. The next thing we're going to deal with is robotic fabrication, but most of the stuff today was robotically fabricated anyway. So almost that distinction is a little bit difficult to sustain. And also between the kind of the digital and the analog, we saw that, I mean, first of all, I want to say thank you for all these presentations. It's great to see things coming out, not necessarily from London and New York, but from Iran and India and so on. But in terms of the Iranian fabrication thing, it was a kind of human computer interface, right? It was both human, it was both analog and digital together. And I think even if you're working computationally, you're using algorithms, there's always a human component, because if you don't like what comes out, you just tweak the algorithm, right? I mean, so you can't necessarily just talk about the digital versus the analog, or indeed the robotic fabrication versus computational design. It's kind of all together in some kind of way. So Sina, maybe the question to you is, what is the difference between, in terms of category, between computational design and robotic fabrication? How do you make that distinction?
You're asking me?
Yes.
I think research in the field of robotics is really strong, and architects needs to be more involved to push the industrial application of robotics in architecture. But I think when it comes to architectural design, this component of fabrication and materialization is really strong. So when we want to establish an integrated system, therefore, it would be inevitable to consider fabrication components as a feedback to computational design. So, for instance, in the last presentation, we see how the process of self-assembly, which also reminds me of the cover book of John Fraser's book, which discussed this idea of bottom-up self-assembly architecture. So I think this component of fabrication and assembly is a part of computational design. But I assume when we move to robotic fabrication, we would sort of see more about what's going on in terms of the actual research in the field of robotics and fabrication. But yeah, it's sort of impossible to separate these two. Maybe since we discussed this idea of craft and human, I'd like to know more about the projects that Bhavleen and also Farzaneh present. I think this idea of human and craft was really strong in both projects. Maybe you can elaborate a bit more on that.
Yes, as you said, we used collaborative human and robotic fabrication. And in our point of view, it's not necessarily always need to use only robots. I think we can use these machines and tools to help us in our design. Or fabrication process. And when we as I showed in one of my slides, when we wanted to use a completely automated process by using a glued roller, we encountered some problems, and then we decided and understood that a human collaboration would help this process to have a better final result and have a more precise, maybe more precise installation.
Bhavleen, you want to add your music?
Yeah, I guess for the project squaring the circle, the material played a lot of important role. The material demanded it to be stitched and put together in panels, and so was the geometry. Unless if it was a different case where we had a robotic arm, then we would have preferred doing the knitting with the material. So it's the whole workflow of how we wanted to produce with that material. Since the provided material was the fabric, there was a context of what the budget is and how do you kind of use the local craft and local resources. The project demanded that whole method to be done by a tailor. So yeah, I would say that it's really up to the process from its concept model to its final stage of the mock-up. Yeah,
really interesting.
Maybe I could jump in here and continue with another question to Bhavleen, related to the point of time. So we are discussing about fabrication and assembly in this relationship between humans and machine. And I think it was very fascinating to see in your presentation how you later explained that the assembly took very short time, and somehow the process of fabrication and the whole design of this wonderful installation had been conceived to be extremely fast, if I understand correctly, to be installed. No? So maybe if you want to expand a little bit more about these considerations during the design process about the time of stitching and assembly.
Yeah. So like I was just earlier saying, that if it would have been a different scenario, then knitting of the fabric with the similar kind of panels that came out of what we did as a process was that we had to cut the panels, unroll the whole process, unroll the whole mesh. The ideal scenario would have been, given a better machine, I would have done like a knit project, like how you have the knit candela project done by ETH and ZH Code, where you are knitting the whole process in one go. So that would have definitely saved the time. If that's what you're addressing, yes, definitely the assembly part and the installation and the uninstallation process was very, very quick. The maximum time and the labor went in marking, in stitching, and making sure that each seam is properly stretched before stitching it. So these kind of smaller things were definitely time consuming.
Great.
Yeah, I hope I addressed it. Yeah.
No, maybe now that we are mentioning the idea of how you conceive the time in your design, I will ask you with, maybe to the Hyperloop design, the last design that we see, and before the last one. But maybe I want to ask about how do you consider the time scale? I mean, maybe if you try to think in a simulation process, how you consider the time scale in your designs. Maybe if we can, or if you consider it interesting, or you are interested in move on to a intelligent decision-making design, for example, as this idea of simulation, maybe in urban design could be easier to be answered, but also in the process of how you build what you build, it could be involved, because we are always thinking about the time in the design, the time in the construction process, but we don't consider the time when the building is there or when hardware designs is there. And that's why I was referring with the idea of assemblage, more than a cultural assemblage, an economical, social assemblage, or even geographical as well. That's why I wanted to redirect my question to that place, considering this new, idea of time scale.
Mm-hmm. So basically, like when I was actually reading about this movement of discrete, let's say, like, and discreteness, one of my critics about it was actually, it's like, what is the time span and what is how is it going to be more economical? Because what they're actually arguing is one of the good factors about being discrete is it's going to be more economical. But in what case it's going to be economical? And like if I'm going to go back to what Sina was telling us about the standardization of them and how we can control this assembly. So I cannot completely ignore the fact that being discrete is everywhere, like, and it's something that it exists in everything. So also, if we consider the molecular level of the continuous materials, yes, but if not, let's say like projects that we had today were completely discrete, but if we're going to 3D print something, I'm going to call it continuous. But if we're going to talk about the assembly of them, what discrete projects are talking about is to decrease the degree of freedom in the form. So we can actually have, let's say, 5 different modules. But in the assembly of the normal fabrication, we can have up to 1,000, let's say. So in this case, they're going to say the mass customization is going to be easier. So we're going to only have like a pipeline. So we have 5 different elements. That's going to be faster and more economical. If I think
you're actually referring to this factor of time is really interesting. Thanks, Marina. I think we can discuss this further. But what you're referring to also is about like simplification versus rationalization, right? So how we can simplify, but how we can rationalize. I think these two are different to a certain extent. And but back to this idea of time. I think somehow this idea of time, we can think of time during the assembly process, but also we can think of time the way you're addressing, referring to cultural and societal aspect. I think somehow was also addressed in the last presentation, where we are discussing a sort of user-driven customization. So the user is involved, and then this helps us to sort of customize our design throughout the times. Maybe considering the factor of time as a kind of societal and cultural factor, the last group can also sort of reflect on that. How do you see the role of time?
So for us, one of the main points is actually designing within the time. Because when we think about the architecture, it is mostly creating a static structure by using the past data that we already have and creating something that won't change anymore. So we are creating some sort of a monumental structure that do not really have that much possibility to change or flexibility. That's actually the main part that we are trying to change, like trying to create a reconfigurable building. For us, discrete is just a tool that we are using here because it kind of makes it possible to reconfigure the building that we are creating. I think that this reconfigurability is, especially this year, I would say, is getting more and more important. When we think about it, the state of architecture and the building currently, in this situation of coronavirus, for example, the only thing that we could have done in this situation was just closing every building and closing ourselves in our homes, instead of being able to adapt our buildings to what is happening. So in that case, I would say what we are trying to do here is actually integrating time as a dimension of design in our building, in our structure that we are creating, instead of just trying to create something that can stand against the time, instead just designing something that will exist with the time.
Great.
Yes, but can for example, an interaction of the emergent effects that our building have reinform our designs really can do it. I mean, I'm just asking you because I'm really interested about this, and also maybe I think that in the case of the design of the digital production, it was only, I think it was the only one who goes really deep in terms of affection, for example, in terms of how can interact with humans more than what you are exposing in a way, because it has like more flexibility, not only because it's not going just to the idea of put one things another things. It's more flexible. So the matter is thinking more in the idea of a membrane and the idea of an envelope, but are more interested in this idea of multi-layer things that what we designs, our designs have. So that's why I think maybe in that design you can see it better. I don't know what you think. Maybe I'm wrong.
If you talk about the flexibility, when we talk about the flexibility, the point that we are saying is more about function, like functional flexibility instead of structural flexibility. And the human interaction in this process is, so we want to integrate the user feedback into the formation of this building, actually, because when we think about it, the users do not have any sort of control over the building, even though they are the ones that are directly getting affected by how the building is functioning. This is the kind of interaction that we are trying to provide, because we think that the user is one of the main characters here, even though in the static structures, they do not have any sort of effect other than, you know, being able to change some part of the interior, etc. I'm not sure whether this answers your question, but
that's okay. It was more a comment. That's okay. Thanks.
I think I just wanted to comment because I think, you know, we've been talking a lot about the discrete, and I think just to help out in the discussion, I think sometimes this discussion about the discrete is kind of circumventing a bigger problem that we kind of haven't addressed and maybe should be addressing, and that's been kicking around, which is the problem of form. And I think, you know, Christopher Alexander has this interesting quote where he says the real object of discussion is not form alone, but the ensemble of form and context. And I think, you know, I want to actually say that, you know, I mean, I think he's really interesting thinking about the underlying logic. And I think a lot of you actually talk a lot more about that than you give yourself credit for by going back to the discrete. And I think, you know, the implications that a lot of your projects show and talk about in terms of future scenarios of these projects coming into our society are actually really interesting. And yeah, this is more a comment than a question to all of you, but I think I just wanted to bring up this discussion that I actually think is very important in terms of architectural design, which is form. And I think the discrete is kind of like circumventing a deeper discussion that we might want to have in architecture more.
Yeah, very well said.
Hello.
But finally, are we coming back to the tectonic idea with this? Because robotic fabrication tends to put one thing in another, so it looks like we are coming back to the tectonic idea again.
I think you're right. Maybe we come back to this. Ahmed has a question.
Yes, right.
Yeah. For Amin, your pavilion was amazing, and the plugin, I remember I explored it before. But in your presentation, there was a photo where everyone was standing on the pavilion. So how the connections can have all these loads on the pavilion? It's a wooden connections. But did you optimize the structure or do some kind of simulations? What you have done so all of these people can stand upon the pavilion and it's still not failed?
Yeah.
Yeah, exactly. Thank you for your question. It's a great question, actually. As I mentioned, we are a sort of interdisciplinary group, so I'm not into, let's say, civil engineering and also this kind of, calculation. But yes, you're right. There has been, many, tests, about this. Let's say the structural analysis of this project. Yes, you're right. I don't know exactly. I don't remember what you, which project you may mention. Recycle shell, right?
The arc wooden. Yeah.
Exactly. Yes. Since we are, actually the TSI, the recent project that I mentioned at the beginning of the in the beginning of the lecture, it is trying to integrate this structural analysis into the design to production system process or loop. So what you said is true. There has been many, calculation and optimization process behind this fabrication, design to fabrication process. But what we are practicing now is we are trying to integrate this. You know what I mean? Because, I have studied about this process, design to fabrication, design to production system. Even Sina, his papers about materialization, we have, I think, we have the computation to, the process is very simple, computational design to digital fabrication or production, okay? But during this process, we can consider material system, okay? We can consider structural analysis. But what you discussed in the beginning about the time, automation or something like this is very interesting, because what we are talking about is not just about, parametric design or I don't know, or digital design, whatever. We are trying to optimize the design based on our needs. According our demands. One time is one of them. Okay, so the automation is required. I can refer to the lecture of Abir Gramazzi about digitization. Okay, it was like something. It was mentioning that 10 years ago, no one cares about digital tools or means or something like this. But now, maybe they don't like it. They don't even like it, but they have to use them. Okay. So when we talk about the project, something I showed you, we're not really into forms or geometry or shapes. Let's say, as for example, when I was teaching here in Iran, my studio was focusing on conceptual design thinking. Okay, the student project I showed you at the beginning of the lecture was very simple, but they had this concern about parametricism, digitization. In a way, I call it towards automation. That's it. I'm not really. I hope I answered you. Maybe it was a general.
What software used to optimize structurally the connections? This was my question.
Again,
maybe you can
for the.
Maybe I could add something in addressing your question. Based on some researches which I've recently been studying, there are some software like Sophistic or any discrete element method softwares that are specifically that have specifically been provided for the analyzing the wood-wood connections and analyze their behavior against the wind load or against their dead load. And of course, one of the Professor Christoph Robler's paper was exactly about this question, who used the discrete elements method to analyze the wood-wood connections and analyze their behavior under the applied loads.
Yeah, I think it's actually you brought up a very interesting term like the finite element method or discretization. I think this idea of discretization is also as also Victoria mentioned, is kind of taking away the core of our discussion in computational design. We may use like finite element methods for analysis, and if you think of performance-driven design, the way, for instance, Michael Hensel is addressing in many of his papers, it is inevitable to use finite element methods because you have to discretize your world in order to evaluate your design, whether you are using like structural analysis, like the way we see in the last presentation, by optimizing, for instance, an element, or if you use like solar analysis, you are also discretizing your world in order to be able to evaluate the design. So I think partially this is about the methods, as you mentioned, the finite element methods that we may use, and I don't think it's a style, or it should not be received as a style. Back to this discussion about time. I think many of the projects were addressing this idea of assembly to a really great extent. And I remember that we were in a conference where Mark Berry was presenting, and it was almost like 7 or 8 years ago, and he was mentioning that the next, let's say, focus of computational design and fabrication should be and will be on assembly. And I'm not surprised that today many of the research projects are focusing on this topic. And I think it's really relevant and important, and I'm happy that we were able to see this in different scales. And back to the idea of tectonic, which Marina also mentioned. I think this is also important to address, because we are in the computational design sessions, and this idea of tectonic and ornament is also something that I think we need to sort of cover and discuss. So, and we see a different way of, let's say, considering this idea of tectonics or ornamentation in these projects. So maybe we can pick up on this topic, and some of you can reflect on this idea of ornamentation and tectonics.
Could I just add something to that, Sina? I was particularly interested by Amin's presentation, which kind of situated itself between the world of ICD, of the timber kind of exploration that Akim and others are doing, and then the kind of Philippe Bloch world of Elaheh, with the kind of like the, I mean, I don't know whether we use Rhino Volt for that, but my kind of, in a way, my question really was about, because Philippe Bloch, when he's making his things, is using largely ceramics or stone or something, compressive only members. But Amin was using timber, and timber has this tensile capacity, which can be explored in some ways. And so my question really was, why was it made out of wood, timber, that vault? I mean, it's a beautiful work. And whether one could exploit the tensile capacity of the fibers and the wood in the way that Akim and, say, Dylan Wood has been doing. Yeah, I mean, I think it's a very interesting work. It's very European in a way and very beautiful. Yeah.
Yeah, as you mentioned, it's a great question. Why wood? Because at the beginning, I told you that I mentioned that wood construction. We are going to have a renaissance for the wood of the wood construction. Okay, because it's there are many criticizing. There are many papers criticizing. Articles criticizing this. Let's say renewable, why we don't use renewable energy or this kind of material and construction. Okay, and I think one of the most important reason is that. It's about we can discuss this material from different aspects. For example, from the sustainable point of view, environmental, economic. You know, as you said, for example, Kaiserslautern. Located, TU Kaiserslautern, located in front of a very large, jungle, full of woods. It's when you see this potential, so why not? I mean, but to say, why did we use the wood for the shelter, for the shell? Okay, it has a long background, because it's not really easy to design a shell, okay, with the concrete, or I don't know what you mentioned, flip block is doing it at the edge. But here the process is much easier and faster, because the process we are working on is to create a sort of loop that we can design a shell, whatever, design a very simple model in a CAD method, and considering the fact that it is timber, so we know the behavior and mechanical properties of the timber, okay, and then we have just quickly for I don't know 10 minutes. 15 minutes, we can have these panels, okay, and then quickly we can assemble them for 2-3 hours. I think it's not really easy to make a shell which is sustainable, economic, and made by renewable, resource, and in this fast way, such a fast way, I think it's there is a long. I mean, we are seeing promising future for the project and research is what we are doing at DTC, because I think this world needs researchers something. I mean, like this. Of course, I'm fan of flip block, and you say Akin Menges. Exactly, you're right, because Christopher, who is the director of VOS of the DC. He has been at ETH, he's been at EPFL. I don't know if you heard about IBS. Okay, read about his thesis. It's amazing, because I showed the project in the beginning of the presentation. The theater they made. And Switzerland is amazing from the architectural point of view, from the constructional point of view. If we talk about time, if we talk about the material, if we talk about what it doesn't. I mean, it's just amazing, because as I mentioned, wood is something like I don't want to say gold, but it's precious. It's because, and if you live in Europe, for sure, you know that the wood is the best material for the future of construction and architecture.
Don't get me wrong. I'm not questioning that wood is a sustainable material. Of course, it is. I'm just wondering why. I mean, because timber has both tensile and compressive properties. Maybe one could have thought about, because that was a compression-only structure pretty much, apart from the joints, I guess. I'm just wondering whether one could have pushed it further in terms of wood, because you could have done that with stone or something like that. I guess that was my question simply.
I think it's it's a very relevant comment, and I think this may also be considered as a hint for future works, because I know that some of the works by DTC are looking into this idea of folding structures, where we have this actually combination of tensile and compression forces, and I think this can be a very interesting further topics to be explored. So as we move towards the end of the session, maybe I would like to address back this idea of tectonic and ornamentation, and I would like to directly ask, for instance, the last groups which they were looking into this idea of bottom-up assembly, and also the presentation by Adib, where we see a really strong drive to create basically surface tectonic. How do you, I would start with the last presentation. How do you see the role of tectonics and ornamentation in computational design? Georgia, you want to add something maybe?
Yes, for example, specifically in our project, we try to use the properties of each separate material to enhance, for example, the appearance of our created unit, but this also has functional uses every time. But we took advantages of the color, for example, of the wood or the TFE or the cross components, and we tried to create some patterns into the tiles that they're gonna be assembly. So we try to use this aspect of the materials to create a unified structure with some pattern that it had also functional meaning.
Yeah, so I see in both projects that the process of materialization starts really early in the design process. So it's not like that we have a form and then apply a certain materialization strategy and tectonic to it. And materialization is really embedded in the process. So I think this is something which goes back to the concern and question of Neil, that why we cannot really distinguish between computational design and robotic fabrication or fabrication in general, because in many of these cases we see that the materialization starts really at the earliest stage of design. And yeah.
Because, I think that you're absolutely right. That I think sometimes we have these distinctions we make between fabrication and design, between discrete and continuous. And I think this other one between structure and ornament is a false dichotomy in some ways. We have to be thinking about both. And I think coming out of postmodernism, when I was a student, we were always focusing on ornament, but traditionally and historically, ornament was also always part of structure, and structures were ornamental. So I think in a way we have to sort of see this as a kind of like as being both, and it's a false distinction. Just to go on further, I think the other thing we often think about is human versus AI kind of thing, and increasingly now people are thinking about those kind of worlds as not human versus AI, but the AI is an extension of the human. So I think it's really much more productive to think about these things in combination rather than isolation. But there's actually an article in Digital Tectonics, which or an interview that I did with Greg Lynn about the structure of ornament, and actually when you think about it, it's a kind of beautiful concept. So I think we should be very careful about making these distinctions.
Yeah, exactly. Yeah, I think that's a really good point to sort of conclude. If there is other points or topics that the presenters wants to address, maybe we can have some comments or ideas from
about this ornament thing that you were talking. I wanted to add, like, one thing in digital fabrication and computational design is about this performance-driven ornament and material-driven, but it also allowing us to take a step further, as Michael Hensmeyer in Digital Grotesque, or these last projects that Anna was doing in ETH, that we can see this, the material is informing the ornamentation, but it's not based on only the performance. It's also an architectural decision that wasn't actually possible without computational design. So this technique of folding the meshes together. I remember when I think Daniel Dillenberger had a very nice discussion about it, and he was telling us it was super hard to compute, that we couldn't actually compute it, and we only contour crafted it and fabricated it. So it wasn't possible without the computation. And I think it's really important to see, like, how we can take a step further from only being material, like performance-driven and structural-driven ornamentation. And how can we actually add an architectural level to it?
Yeah, really interesting.
Yeah, I mean, maybe that is. I mean, I think the problem was that I saw in the history of architecture has been both the focus on just ornament and also the focus on just structure. Because, I mean, when I was teaching at the AA with people like Mike Weinstock, I mean, fantastic work they were doing. But they were talking about performance and always in denial of the aesthetic side of things, you know, and you get both sides. You get people just talking about aesthetics and forgetting about material behaviors. And you also get people talking only about material behaviors, somewhat disingenuously, while the whole time they want to produce something that is elegant. So it's kind of like a really interesting kind of balance that you need to have.
Exactly.
Can I just make one kind of comment? I think, you know, one thing I found really interesting about today's presentations was how so many of them came from the periphery, as it were. I mean, traditionally, we've been in a situation whereby all the ideas come from, I don't know, New York and London and LA and something. And actually, we've seen some work being produced in India and Iran and things, which is very kind of gratifying. And in many ways, you know, it's what's really kind of nice about this thing is we're kind of embracing the whole world in some sense. And the world of computation is bringing us together. I mean, this is an astonishing thing. So I just want to kind of like, in a way, make a kind of just an advertisement, say, for next week, where actually we have someone from India, Sanjay Sama, and someone from Iran, Nadir Tehrani, and a few others, working together and talking about how the world of education is opening up because of the domain of the digital. And we have a discussion. I mean, Sanjay Sama is actually in charge of the MIT Open Learning project, which is about basically democratizing education, you know, and spreading the word out there. And you know, to my mind, it was great to see these presentations today, because they were kind of talking about a different sort of modality whereby it's not the center. It's like the world has been kind of the word has spread out, and we're getting these little clusters of interesting kind of pockets of research going on all over the globe. And this is something I think we need to push further. So next week's one is going to be about how we can see how this domain of the digital can help to kind of democratize and spread ideas. But it was a fantastic articulation today of what is possible.
Thank you very much. Maybe I just pick up on that topic and to conclude the session. I think this idea of democratization of education is really interesting, and I'm sure that in the next session we are going to have interesting discussions. I would also like to give credit to Amin, who was actually organizing in 2019 series of lectures by really known scholars in Iran, inviting people from Yale, Harvard, MIT, and I think this idea of democratization was happening to a certain extent a lot, and now it's becoming a must. And I think this is something that we need to embrace, and I think Digital Futures is trying to embrace that. And another point I think which relates to this topic that we addressed today, which also connects to education, is this question of how we can sort of redefine the role of fabrication, hands-on work, and craft, like the way we saw in some of these educational projects in this situation that we are living in. I hope this can be addressed to a certain extent and discussed in the next session. And to a certain extent, we are already discussing this in our sessions. So with this, if there's no any other points, we can close this session. Is there any other points from the committee or?
So, you know, I would just simply say that actually, as background for next week's discussion, it'd be useful if people had a look at the panel discussion we had during Digital Futures World, where Nadir Tehrani chaired a session with Hashim Sakis, Ila Berman, and Eva Franch about the future of the university, and it's very much kind of connected to that. And what was so interesting was the theme of democratization came out throughout in that discussion. So we kind of be building upon that, but it's part of the same debate.
Yeah, great. Okay, with this we close our session. Thank you everyone for joining. It was a great session, and we would also like to thanks our audience who were with us, and this session will also be available in the Digital Future YouTube and Bilibili channels. Thank you very much.
Thank you.
Thank you.
Thank you, everyone.
Bye.
Thank you.
Thank you.
Bye.
Everyone.
Bye.
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 Thank you. Bye-bye.
Bye.
Doesn't fit.